everyone. This is Monica Lupion, and today I will finish the lesson Unsteady State Conduction. This is part of the online course CE 318 Heat and Mass Transfer. If you remember from previous presentation, I already covered a brief introduction about the concept of unsteady state conduction. That is, when the temperature is also a function of time. And we discussed about the different ways to solve the general equation. In particular, we talk about analytical methods, then graphical methods, and finally numerical methods. We cover in detail 2 out of 3 different scenarios that we consider for the analytical method. If you remember from previous presentation, the first case that we studied was the heat transfer with a very small internal resistance. In that case, we can directly integrate the general equation. There is no dependence with the position. So we have an uniform temperature within the solid or within the fluid. And after the integration, this is the solution of the general equation. Since the internal resistance is very small, when we defined the Biot modulus, we also find out that this Biot modulus has to be very small as well. The criteria that we define is that if there is a Biot modulus which is lower than 0.1, we call a lumped system, and this is the solution that we can directly apply. Then we study a completely different case. Instead of having a very small internal resistance, there is this case when the surface resistance is very small. In those cases, we can consider that the temperature over the surface of the fluid or the solid is constant and is equal to T infinity. Since the surface resistance is very small, the Biot modulus in these cases has to be very large. So that's what we covered so far. In the class today, I will talk about the situation when we have both internal and surface resistance. As you can imagine, these systems are normally more difficult to solve because we can't really simplify the problem. We have the 2 resistances, the internal and surface resistances, so we can't really do anything about it. However, depending on the geometry, and also if we consider, for instance, just one dimension, there are different situations when we can really solve the problem. For those problems, it's important to clearly define the boundary conditions. So I would like you to go through some of the examples in the chapter 18 and ask yourself if you know how to define the different boundary conditions. This is just an example here, and it's important that, well, this is the initial conditions, but then once we are in a given time is equal to t, then in x equal to 0, we have a certain temperature, and when x is equal to L, then there is an insulation here, so the heat transfer rate is 0. So those are the type of things that you really need to know how to apply. And the only way is by training. That's why I think it's a good idea if you go through the different examples in the book. We will also practice with some examples and some exams from previous years. In general, the analytical method comprises different steps, the application of different mathematical tools. We talked already in the previous lessons when we covered steady state conduction that one of the most common methods or mathematical tools is the separation of variables. So first of all, we need to simplify the partial derivative differential equation, then try and error to convert the partial differential equation to an ordinary differential equation, because in general partial differential equations are very difficult to solve. Then try and error to determine the constant from the integration of the ODE, and then apply the boundary conditions. And finally, the initial condition. So those two, normally the initial condition is easy to identify, but the boundary conditions can be tricky sometimes. Right, so we already covered the analytical method for steady state conduction, the three different cases that I just mentioned. If we have either very small internal resistance or very small surface resistance, those two cases are more or less feasible to solve. When we have both internal and surface resistances, then the problem will get more and more complex. So is there anything we can do to avoid all these mathematical tools and all these calculations? And one option is the graphical method. We're going to be using the charts in Appendix F. Those charts are called Heisler charts. And the way we use it is by defining four different parameters: y, x, m, and n. The relative temperature change is defined here. So y is equal to the temperature in a certain position minus the temperature over the temperature minus the initial temperature. X is defined as the relative time, and it's equal to the thermal diffusivity times and over the position square. The relative resistance is defined by the letter M and is equal to the thermal conductivity over the convective coefficient times the position. And finally, N is expressed as the relationship between X and the position either in the center or in the H's, depending on the problem. We're going to see some general examples here in the class today, and also I have prepared a few examples to share with you about how to use these charts. But it's relatively easy. It's very intuitive. If you take a look to the Appendix F in your textbook, you will see a number of different graphs. They are, depending on the geometry, we have different charts, but they look very similar. So in all these charts, you have y here, which depends on the temperature, and x here, which depends on time. So there is a relationship between temperature and time. Then, depending on the parameters m and n, there are different lines here. So you need to identify which line are you in, and then it's as simple as, let's say that m is equal to 0 and n is equal to 8. So we should be here over this line. And then if we calculate x, and x is equal to 2, you just have to go up the intersection and then go left. So the parameter y will be around 0.018. And then if you have the value of y, you can directly get the value of the temperature. It's important that in addition to look to the chart and know how to use the chart, it's important that you pay attention to the diagram that is normally included in these charts. It gives information about the relative position and how x1 and x are defined. Like in this case, for instance, the reference is the center of the flat plate. So x1 will be half of the thickness of the flat plate, and x will be starting from the center of the element. Same thing for cylinders, for instance, and as I mentioned, you can see the graph here with the same elements, x, y, and the lines m, and depending on n as well. And if you pay attention, you can see the diagram that I just mentioned with the values of the position. In this case, x1 is the radius of the cylinder, and x will be starting from the axis of the cylinder. This is the case of a sphere, and as you can see, it follows the same procedure, the same look. So, in general, graphical methods are easier, but they are limited. And there are 3 different assumptions that we need to take in order to be able to apply the charts. One is that we need the Fourier's field equation, or the Fourier's second law, to describe the process. That means that we need to have a constant thermal diffusivity, alpha, and also that there is no internal heat source. Second condition is that the medium has to have a uniform initial temperature T sub 0. And finally, the third condition is that the temperature of the boundary, or the surface, change to T infinity when the time is equal or larger than 0. So those 3 conditions are critical to apply this graphical method. What happens if we have some combination of geometry? So there is a case that is not exactly as the geometry is defined in Appendix F. Well, we can still solve the problem and we can still use the graphs. We combine the graphs, we combine the different charts in order to get the geometry that we're looking for. 3 examples. Let's say that there is a rectangular bar with isolated ends. Then we calculate the y that we use to get into the chart for the case that the position is equal to one h and the other position is equal to the other h. And then the parameter y of the rectangular bar will be just ya times yb. Same thing when we have a 3D rectangular parallelepiped. We can calculate the parameter y by just multiplying the different parameters y over the three surfaces of the rectangular parallelelepiped. Another example, the final example, if there is a cylinder including both ends, we calculate in one side the y directly related to the cylinder, and then we multiply that value by the parameter y related to the ends. You can see more clearly here what I meant. So if there is a three-dimension case, like this one, we can directly combine the parameter y of these 3D elements will be equal to the parameter y of the surface x, surface y, and surface z. For each of those, we need to calculate y, x, m, and n, and use for each of those, or each of these, use the charts to determine the value of y, and once we have the three of them, we can directly solve this equation here. Okay, and to finalize these lessons, I would like you to stop the video for a few minutes and read through the problem. I will solve this problem in a tutorial video, and I will, so you will be able to see how to solve it, but I would like you to try first and see if you're able to solve by yourself. So in summary, about unsteady state conduction, we know that unsteady state conduction means that there is a dependence with time. We went through the three different methodologies to solve the general equation for unsteady state conduction, focusing on the analytical method and the graphical method. As for the analytical method, we study three different cases when the internal resistance is very small. Those are the systems that we call lamp systems, when the Biot modulus is lower than 0.1. And in those cases, we can directly use this equation here as a solution of the temperature. Then we also study when the surface resistance is very small. And on those cases, the temperature over the surface is assumed constant and equal to T infinity. Those cases are defined by a Biot modulus very large. When we don't have, if there is a case when any of those conditions are met, then we need to solve the general equation using mathematical tools, or we can also use the graphical methods. There were a few conditions that the problem needs to meet, but if the conditions are fulfilled, we can directly use the highest layer charts that is in Appendix F in your textbook. We define four different parameters, y, x, m, and n, and we're able to find the relationship between the temperature and the time. And finally, we also study what happens if there is a three-dimension problem. In some cases, we can use the graphical method to also solve more complex geometries